Okay, here we are in chapter 6 talking about enzymes, and of course probably half at least of proteins are enzymes. So that's a lot of proteins, and this is one of the main things that they do is catalyze reactions. So enzymes are the catalysts of nature. Most of these are proteins. There's a few RNA-based enzymes, but they're mostly protein-based. And in a few cases, the protein can be enhanced by special molecules we call prosthetic groups or cofactors, which allow them to catalyze other reactions that the amino acids themselves would not be capable of. As you saw in hemoglobin, of course, there's no amino acid that can bind oxygen very well or at all. So heme would be a prosthetic group for hemoglobin. Now, all catalysts speed up a reaction by lowering the activation energy. And in the case of enzymes, these are catalysts that are very specific in terms of which reactants they bind and which reaction they catalyze. We think of the reaction taking place on the surface of the enzyme, usually in a special place that we call the active site. But of course the equilibrium is not going to be affected by that, because the equilibrium is determined by the free energy of the reactants and products, so delta G, the difference in free energy, that will determine the equilibrium. And all the enzyme does is change the energy of the transition state, that is the highest energy state between the reactants and products. The uncatalyzed reaction, you have a barrier like this. The catalyzed reaction, we have a barrier that's lower, and therefore it's easier to get the reactants to that energy, to that transition state, than it would be for a higher energy transition state. So the transition state is essentially, we define that as the highest energy state. That's going to be an intermediate that the reactants have to go through on the way to becoming products. So there are probably several, of course, intermediate states, but the transition state is the one where the energy is at a maximum. And so that's going to be the highest barrier. The activation energy, delta G double dagger, is the difference in energy between the ground state of the reactants and the transition state, okay, at least for the forward reaction. And the larger this is, the less likely the reactants will be at the transition state, and so therefore the slower the reaction. Enzymes catalyze a reaction by lowering this barrier and therefore making it more likely for the reactants to get to that point. It's also because catalyzed reactions, the transition state usually is not the same transition state as in the uncatalyzed reaction. Therefore it gives you an automatic mechanism why the energy would be different, because it's not the same transition state. And like I said before, the place where the reaction is taking place on the enzyme, we call this the active site, and when the reactants are bound there, we call them substrates. Alright, so now we've essentially changed reactants to substrates, and here we're considering the uncatalyzed reaction. That rate is going to be the difference, is going to be related to this barrier here, the difference in energy between the substrate and the transition state. For the forward reaction and for the reverse reaction, it'll be the difference in energy of the products in the transition state. In this case, since substrates going to products is favorable, the reverse rate will be slower than the forward rate, but they'll both be pretty slow. The equilibrium, of course, will be determined by delta G. In this case, delta G not prime, the way they've written it here. I guess if everything is 1 molar, that would be the case. In the case of a catalyzed reaction, we have these other intermediate states. For example, enzyme substrate bound to enzyme. We have an enzyme substrate complex. Substrate going to product on the active site. So now we have an enzyme product complex and then enzyme releasing product. Notice the delta G of the reaction has not changed because we start with free substrates and we start with free products. But now the highest energy state along this enzyme catalyzed trajectory is going to be lower in energy than the highest transition state, or the highest state in the uncatalyzed reaction. And this is going to be the rate that determines, this is going to be the barrier that determines the overall rate. And so therefore we have a higher rate, a faster reaction. The difference in energy between these two transition states we can define as delta GB. This would be related to the difference in rates. But I'm not really going to get into that. Here's a different picture of the same thing. Probably a little more realistic picture, because if enzyme binds substrate, the enzyme substrate complex should be lower in energy, right? Otherwise it wouldn't bind. So this is actually a better picture. So you kind of go into a little bit of a barrier, a little bit of a well here. And so you've got to go higher up to get to this transition state. But that transition state is still lower in energy than substrate going to a transition state by itself. So this barrier here from enzyme substrate to enzyme transition state is still smaller than going from non-enzyme bound substrate to transition state. That would be this delta G, okay, the non-catalyzed reaction. So we can define a equilibrium constant for the reactant going to transition state. So it's the transition state over the reactants, and we just basically define this the same way we did delta G's and KEQs. This is now the KEQ, the equilibrium constant for the transition state. This is going to be a very, very small number, okay, a tiny, tiny number, because this is a very unfavorable reaction to go from the ground state of the reactants to the transition state. We can define the rate constant of a reaction as K is kBT, the Boltzmann constant times temperature, over the Planck constant. That kBT over H is about 6 times 10 to the 12th per second. But we're going to multiply that by K double dagger, which will be a very, very small number. So we're multiplying a very large number by a very small number, actually a really, really small number. So this rate will be, well, it depends on what this product is. And that's the rate constant for the reaction. We're going to get more into chemical kinetics here for a second. So if you have a simple first order reaction, that's so basically it's first order. The velocity is going to be the rate of increase of product over time, or the negative of the change in reactant over time, because of course that's going to be a negative rate, right? I mean, reactant's going to go down as product goes up. So if we were to draw that out, so if we had change in concentration over time, product would be going up, reactant would be going down. Although it won't look linear like I've drawn it here. It would actually look more like this if it's the first order rate. So product would be going up like this, and let me just pick a different color for reactant. Reactant would be going down like this. So a first order rate depends upon only one concentration. We'll get into second order rates later. So more realistically, of course, we don't just have one rate. We have a forward rate and a reverse rate. So usually K1 and K minus 1. So the velocity of the reaction, the rate, is going to be dP over dt, which is going to be K1 times reactant concentration minus K minus 1 times product concentration. That is the rate of the forward reaction. So dP dt, actually wait a minute. So this rate here is just going to be K1 times the reactant concentration. So the rate of reactant going to product, the rate of product going to reactant is just going to be K minus 1 times product concentration. Okay? So the overall change in product is going to be the rate of forming product minus the rate of product going back to reactant. Okay? At equilibrium, those two rates will be equal. So this will be true. The equilibrium concentration of reactant times K1 will be K minus 1 times the equilibrium concentration of product. If we do the ratio of these, we'll get K1 over K minus 1, which, of course, the equilibrium constant of P over equilibrium constant of R is just KEQ. So this is just another way of looking at KEQ. And it's also the same as the ratios of the intrinsic rate constants. We can have second order rates as well. Notice that with this reactant here, it's not automatically going to be K, a rate constant, times A times B. You'd have to determine the order of the kinetics by doing an experiment. It might be K1 times A. It might be K1 times A squared. You really don't know until you do the work to determine the order of the rate. Same here, if it was simple, the forward rate would be K1 times A squared. Again, you'd actually have to determine that experimentally. Okay, so with enzyme catalyzed reactions, the amount of the catalyzed reaction will be dependent upon the amount of enzyme, obviously, we can pretty much just ignore the uncatalyzed reaction because it's going to be so much slower. I mean, if it was fast on its own, you wouldn't need a catalyst, would you? Right? You only need to catalyze things that are normally slow, happen slowly. So, like I said before, the catalyzed reaction will take place at the active site. This is the place where the reactants bind the enzyme and then are transformed into products. So let's imagine a very simple reaction. We have an enzyme binding substrate, forming the enzyme-substrate complex, and then it's going to be converted to product and released. We could actually come up with enzyme product goes to enzyme plus product and have another K3 and K minus 3, but here we're trying to keep things as simple as possible, okay? So we imagine that the reaction goes like this, okay? And we can make it even simpler if we confine our analysis to the initial rate when there's no product. That is, you mix enzyme and substrate together. In the beginning, there is no product, so concentration of product is 0, which means enzyme plus product going back to substrate is going to be 0 because the product concentration is 0. That allows us to define the rate of formation of the enzyme-substrate complex. Okay, there's only one way to form it now because you can't go backwards from enzyme plus product. Sorry. And that's going to be K1 times E times S. That's the forward rate. Once you've formed enzyme-substrate complex, there are two ways to get rid of it. One is to go back to enzyme plus substrate, and the other one is to form product. So let's start with the simplified version here. So now K minus 2 is pretty much 0. Well, it's there, but this reverse rate is going to be essentially 0. Okay, so the rate of formation of the enzyme-substrate complex is K1 times E times S, and the rate of disappearance is two first-order rates, K minus 1 times ES and K2 times ES. So K minus 1 is just dissociation, K2 is catalysis to form product. At the steady state, these two rates will be equivalent. That is, the enzyme-substrate complex is constant. So if we set these two to be equal, then we get this relationship here. Enzyme times substrate over enzyme-substrate complex is this ratio of intrinsic rate constants, and we're going to define that as the Km, the Michaelis constant. You notice it looks like it looks like an equilibrium constant of forming the enzyme-substrate complex, right? It looks like an association constant. That is, where the two it looks like a dissociation constant, where enzyme substrate is going to enzyme plus free substrate. But as you'll see, appearances can be deceptive. It behaves that way, but it's not what the dissociation constant is. All right, so what we're looking at is this regime here, where it's the initial rate, but not the very first, maybe second or less. We want the point where the enzyme substrate complex is pretty much constant. So it's going to be formed early on, and now we're at the steady state approximation where the product is being formed and the substrate is dropping. Now, if you go too far out, the product will accumulate and the reverse rate becomes non-negligible. And so the rate of disappearance of product will slow down, the rate of appearance of product slows down, the rate of disappearance of substrate slows down. So we don't want to go too far in the reaction. In fact, this probably is too far. It depends on the rate constants. But usually we want to look at this early part here, but not too early. We want to look at the part where the enzyme substrate complex is constant. That is, this is true here. Okay, and there's not too much product accumulated. So let's talk about the velocity of the reaction. That's going to be this K2 times enzyme substrate complex, right? The maximal velocity is where all of the enzyme is bound to substrate. So enzyme substrate complex is the same as the total enzyme concentration. There's really only two forms of the enzyme, free and bound to substrate, right? So Vmax is going to be K2 times E total. And E total is just the two forms of the enzyme added together, enzyme substrate complex plus free enzyme. Okay? So V is K2 times ES, and Vmax is enzyme total, K2 times enzyme total. Okay, so we can substitute all these things in. The K2's cancel out, and it's just enzyme substrate complex over enzyme total. It's an enzyme substrate complex over enzyme substrate complex plus free enzyme. All right, so we're going to, we have now determined that ES equals E times S over Km, just rewriting this here, okay? So V over V max is ES over ES plus E, so E times S over Km over that, again, E times S over Km plus E. Hopefully you realize E's are going to cancel out now. I'm going to basically multiply both sides, both the top and the bottom rather, by Km over E, so all the E's will cancel out. If I multiply by Km over E, I'm going to have S on top left over, and on the bottom I'm going to have S as well, and plus Km. So this is what I end up with, S over S plus Km. And that's the Michaelis-Menten equation. V over V max equals S over Km plus S, or S, yeah. Okay, notice that when the substrate concentration equals the Km, the rate will be 1/2 the max. That is, you'll get Km over Km plus Km is 1/2. Notice how similar this is to the ligand binding equation? Yeah, that looks familiar, it should. So you get a hyperbolic curve, okay, where when the substrate concentration equals the Km, we're at 1/2 the maximal velocity. And as substrate concentration increases beyond that, we'll approach a maximal velocity, Vmax. That is, V over Vmax will be 1. So, yeah, there's a similarity. The fraction of the maximal velocity, okay, the actual velocity over maximal velocity is S over S plus Km. The fraction for, ligand binding is, that is, as a fraction of the maximal ligand you can bind, it's ligand over ligand plus Kd. Okay, so they're both hyperbolic curves, and they're half maximal when the concentration of the small molecule, either the ligand or substrate, is the same as Kd or Km. So ligand to Kd, substrate Km. So Km is for substrates what Kd is for ligands. Okay. Now,